Hey everybody, so the last videos that you watched were about waves, and today we are going to apply what you know about waves to the topic of sound. Before we get started, here are your homework questions to hand in the next time you come to class. Number 1 is, what is sound? Number 2, what is the speed of sound in air at 37 degrees Celsius? By the way, 37 degrees Celsius is about body temperature. And number 3, why does sound travel faster in water than in air, and faster in steel than in water? So keep an eye out for the answers to these questions. So let's start with what is sound? Well, sound is a mechanical longitudinal wave. Hopefully you remember from the previous 2 videos that a mechanical wave needs a medium. It means it needs a material to travel through. So, in those sci-fi movies where the spaceship explodes in the middle of outer space and it makes this giant boom, that wouldn't actually happen. The boom would not exist because space is a vacuum. There is no material for the sound to travel through. Therefore, there will be no sound. So it needs a medium. What that medium is doesn't really matter, as long as there's matter for it to travel through. And it's a longitudinal wave. So remember, we have 2 different kinds of waves. We have a transverse wave that looks like this, where the wave energy goes one way, and the particles in the wave go perpendicular to that. Sound is not one of these. Sound is a longitudinal wave. So that's going to look something like this. And remember, a longitudinal wave is where the energy in the wave moves one way and the particles in the medium move parallel to that. So they wiggle back and forth parallel to the transfer of energy. Now, in order for a physicist to say that sound has meaning, there must be 3 things. There needs to be a source of sound, a medium for it to travel through, and a receiver to get that wave energy. So the whole philosophical question, if a tree falls in the forest and no one's there to hear it, does it make a sound? According to the laws of physics, it does not make a sound, because even though there's a source and a medium, the medium being the air, there is no receiver there to hear it, so at that point it's just a pressure wave moving through air. It's not classified as sound. But that's getting a little nitpicky. So, a source of sound is anything that vibrates. So this little picture is something called a tuning fork. And a tuning fork makes a pure sound at a specific frequency. And you use it to tune instruments. You can see as this tuning fork vibrates back and forth, it pushes the air around it. Or if this is in water, it will push the water, whatever medium it's on. And as it pushes that air, it makes a longitudinal wave, causing those air molecules to bump into each other in succession until that sound wave hits somebody's ears. Now, we're going to talk about all 3 of these over the next couple videos, but I wanted to give you a heads up of these being the things that we need in order for there to be sound. Now, it turns out that sound travels at different speeds. And it travels at different speeds depending on the medium and the temperature of the medium. So the speed of sound in air is 331 meters per second at sea level, at 1 atmosphere of pressure, and at 0 degrees Celsius. So if we were at the beach and it was pretty cold out, it was freezing for water, then the speed of sound when you were talking to someone would be 331 meters per second. But what about in the middle of the summer when you're at the beach and you're yelling at a friend to catch a frisbee and it's much warmer than 0 degrees? Well, we can actually figure out the speed of sound if we know what the temperature is. So to calculate the speed of sound at different temperatures, you use this equation. You take 331, which is the speed of sound at 0 degrees Celsius, and you add 0.6 times whatever temperature you have in Celsius. So, for example, if we were to go ahead and say that it is 20 degrees out, which is about room temperature. It's between 68 and 70 degrees Fahrenheit. We would use this equation to find out the temperature, and it would be 331 plus 0.6 times 20, 20 being our degrees Celsius. This becomes T equals 331 plus 12, if you multiply 0.6 by 20. So when you add 331 and 20, the temperature equals 343 meters per second. So as you can see, as the temperature increases in air, the speed of sound also increases. So it turns out on a hot summer day, the sound is traveling faster through air than it is in the middle of the winter when it's freezing outside on the campus. Now, it doesn't just matter how hot or cold the medium is, it depends on what the medium is. So the speed of sound is different in different materials. In general, sound is the slowest in gases. So even though sound is traveling at about 343 meters per second in this room right now through the air, if I were to be speaking to you underwater, it will travel much faster. In water, it travels at about 1,440 meters per second. Much faster than in air. And if I were to talk to you through a concrete wall, put my mouth right up to the concrete wall and yell something, the sound will travel much faster in concrete than in water. Now, the reason for this is because sound is a longitudinal wave, and it happens, the waves happen because the particles crash into each other in a sequence. So if I'm over here and I'm saying something, I look like Pac-Man. As my voice comes out, I'm vibrating those air molecules and pushing them forward. So the air molecules close to my mouth will move forward and bump into the ones in front of them, and those will bump into the ones in front of them, and those will bump into the ones in front of them until they reach your ear. In air, our molecules are really far apart, right? This is what air is like. In a liquid, the molecules are much closer together. So the contact between these molecules moving back and forth will be much faster. And in a solid, the molecules are pretty much touching each other. They're right up against each other. So you can think of this as the molecules not having to travel very far before they bump into another one. And that's why sound travels so much faster in a solid object than in air. Now let's talk about some characteristics of sound, because we know that you can make a ton of different sounds, and I want to give you the vocabulary to talk about those. The first term is loudness, and this is related to the intensity or the amplitude of the sound wave. And remember, amplitude is the maximum displacement from equilibrium. So if we have a sound wave like this, and we have the same sound wave that's the same frequency, but the amplitude is much larger, this one is going to be louder. Now, if the pitch were different, that would be because the frequency is different. So that would look like something like this, my original, and then something like this. Now, the second one has a much higher frequency. We can make more cycles every second. That means that the pitch is higher. So a dog whistle, or when somebody whistles really, really high pitched, that's because the frequency of that sound wave is very, very high. Now, let's talk about the audible range of humans. The audible range of human beings is from a frequency of about 20 hertz to 20,000 hertz. So it's a pretty large range. But over time, your hearing will decrease with age. And that's because we end up putting stress on our ear and the mechanisms that turn sound waves into electrical signals in our brains. So some of you may have heard of this before, but they make a cell phone ring out there that is really, really high pitched. And the reason that they made it is because students can still hear that high pitch, but older teachers can't because their audible range has decreased over time. I wouldn't recommend any of you getting this cell phone tone because it's really obnoxious, but it's a really good example of how hearing decreases with age. And you can never get your hearing back. Now, this is a plug for your safety from me, but if you are listening to music, don't turn it up full blast, because every time you do that, you are damaging your hearing, and you can never ever get your hearing back. Once it's gone, it's gone. And you really don't want to be listening to the radio 20 years down the road and not be able to hear certain parts of the music because you destroyed your hearing now. Just putting that out there. The next term is ultrasonic. And ultrasonic is any sound wave with a frequency above 20,000 hertz. So like I mentioned before, a dog whistle has a very, very high pitch because it has a really high frequency. Now, people can't really hear dog whistles. We can hear it a little bit, but not really. The reason why dogs can hear it and they hate it so much is because it has a frequency above 20,000 hertz, which dogs can hear. Their ears are tuned into higher frequencies than this. They can hear ultrasonic sounds. The opposite of that is infrasonic. And I don't know if you know this, but ultra means over and infra means under. So infrasonic is any frequency below 20 hertz. So if somebody comes over to the table you're sitting at and shakes it, and you can feel that vibration but you don't hear it, that is an infrasonic wave. It's something below 20 hertz, so we cannot hear it, but you can feel it. The vibrations are there. And finally, supersonic doesn't actually refer to frequency at all. Supersonic means an object traveling faster than the speed of sound. So if I were standing in this room and the speed of sound is 343 meters per second and someone shot a high-speed bullet faster than that, that gun would be going supersonic. Now, how does the ear work? Well, it's this crazy mechanism of all kinds of things like your eardrum, which you've probably heard of, the three tiniest bones in your body, which are called the hammer, anvil, and stirrup, and the cochlea. All of this, it turns out, is connected to your sinuses. So if you have a really bad cold or something, or allergies, and your sinuses are all messed up, your ears are going to be messed up too. Because this tube right here leads down into your sinuses where your nose is. It's all connected. Now, what do all of these things do? Well, the outer ear is the ear canal, which channels the sound waves to your eardrum. So as the sound waves come in, they get channeled down your ear canal like this, and that's why your ear is shaped like a cone, so that it can pick up and bring in as much sound wave as possible. And when it gets to your eardrum will vibrate back and forth with the frequency of the sound wave. At that point, your eardrum vibrating transfers those vibrations to the hammer, anvil, and stirrup. So those three little bones all work together to vibrate, to transfer that sound energy. At this point, it's still mechanical energy, it's still vibrations. But the next step is where the cochlea changes those vibrations into electrical energy. So this is where the magic happens. All of the sound waves come in here and vibrate the cochlea, and the cochlea takes that and changes it into an electrical signal that gets sent to your brain. And there, your brain takes those electrical signals and thinks, okay, it was this frequency and this pitch and this tone, so it's this sound. And then your brain tells you, okay, somebody's saying hello. All of those steps happen pretty much simultaneously, which is pretty cool. And that's how we pick up sound. This is the receiver end of the three needs for sound. So now that we've talked about that and what sound is, go back to the three homework questions here and answer them for the next time you come to class.